Yes, on behalf of the Faculty of Science and the Dean of Science, Professor Scott O'Neill, I'd like to welcome you to a big science lecture called Chasing the Change. Tonight's lecture will be delivered by two of our very best researchers within the Faculty of Science, Professors Stephen Chown and Professor Doug Macfarlane. Firstly, I'd like to introduce Doug Macfarlane. He's currently an Australian Research Council Laureate Fellow. He's a Fellow of the Australian Academy of Science and a Fellow of the Academy of Technological Sciences and Engineering. He hails from the School of Chemistry and currently leads an energy program which is called ACES, the Australian Centre for Electromaterials Science. It's my great pleasure to welcome Doug. And he will be joined tonight by Professor Stephen Chown, who recently moved from Stellenbosch University in South Africa to join Monash University in 2013, and he is the current head of the School of Biological Sciences. He was awarded the Martha T. News Prize for Science and Policy in Antarctica in 2009, and currently represents the scientific community on Antarctic research at the Committee for the Environmental Protection of the Antarctic Treaty System. Please welcome Stephen to the lectern, and we'll start the lecture on Chasing the Change.
Well, thank you very much, Andrea, for your introduction. The talk is about chasing the change, and I would like to start with two areas of human endeavour that have really intrigued me. The first is performance, that is, individual performance. It informs us about how we deal both physically and intellectually with limits that are set us. Of course, scientifically, I'm interested not so much in the performance of humans, illustrated here by an ABC picture of Anna Mears overtaking her Japanese rival, but by the performance of much smaller animals, ectotherms, and that'll form some of the topic of tonight's presentation. The second area of human endeavour that I'm intrigued by is what Neil Stephenson, the author, called speculative fiction. The reason he used the term and not science fiction is, in his words, because you are as likely to encounter a Cylon as a dwarf carrying a sword in speculative fiction. The important part of it, though, is that it often deals with how human society faces and copes with dramatic crises. In the particular example illustrated here, the crisis is the decline of the human population from 20 billion to 50,000. It's really a large feature of this whole series, but any conservation biologist will realize that humans tend to be quite happy with an order of magnitude fewer organisms before they even start getting worried about their crisis. Speculative fiction has dealt with climate change, at least in my view, really quite well in two recent books. One of them is far more bleak than the other. Both have to do with how human society and individuals in particular cope with a dramatic change in their circumstances. So can we expect such change? Of course, Peter Heller's The Dog Stars really had much more to do with a disease outbreak and then how people cope with the additional stress of climate change. And it was quite a slow and slowly progressing climate that was changing in the novel itself. But how are we doing? Should we worry about what is here illustrated as speculative fiction? Well, if we turn to the facts, it's very helpful that just a few weeks ago, the Intergovernmental Panel on Climate Change released the physical basis report of its AR5, the Assessment Reports 5. Along with the full report and the summary preceded the full one, was a very helpful set of about 8 slides for the media and for policymakers. And what I've done here is just extract a few of those slides from the freely available presentation from the IPCC. And their messages are quite clear. Warming in the climate system is unequivocal. The human influence is clear. And if you go through the report itself, the illustrations are perfectly obvious. So here we have some daytime and nighttime changes in temperature, and the anomalies are pretty clear from the data they present. Of course, as many folk will realize, the IPCC is not the only game in town. What they do is they collate already published information and go through it. So if we look at some of the published information that has emerged since their September release, then one of the most dramatic examples, for me anyway, is this recent article by Camilo Mora and colleagues that appeared just about a week ago in the international periodical Nature. And in essence, they said any of these areas in red and yellow will be outside the kind of 1960, 1991 variability by, well, within about 7 years. And of course, as you get into the green and blue, it'll take a lot longer. For this audience, what's particularly important is the fact that yellow is kind of the populated areas of Australia. So we have evidence that is emerging post-IPCC and lots of evidence continuing. The IPCC set of slides also illustrates why this talk is entitled Chasing the Change. The point is that limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. In other words, if we're to chase it, slow it down, catch it up, haul it in, then this will be required. But we're not the only organisms chasing the change. This year, some work emerged by Jeremy van der Wal and colleagues in the journal Nature Climate Change. And what they did is illustrate for Australian birds the extent to which they'll have to move on an annual basis to keep up with the changing climate. And the maximum is larger than 5 kilometers per year, known as climate change velocity. You might, sitting in your seats, think, well, kind of look at them. They've got wings. It should be fairly straightforward, 5 kilometers for a bird. But that's not the point. The point you have to think about is picking up your household, everything you used to, and moving it by 5 kilometers every year. So you have new predators, new neighbors, new food to try to find. It's pretty hard to imagine for a really smart organism such as ourselves how we do it, let alone organisms that have to cope with all these other challenges without the extent of sophistication that we think we have. So that sets the scene for why we're talking about chasing the change. What I'd like to do in this first section of getting into the talk is to talk about some of the impacts. To preface the talk, I'd like to make it clear that we're not neglecting the fact that humans have influences on the environment in other ways. The Millennium Ecosystem Assessment dealt very clearly with that by identifying 5 major global environmental change drivers. Climate change interacts with these, but that interaction and those drivers are certainly not this evening's topic. I'd also like to make it clear that in the sections I'm dealing with, I'm dealing mostly with temperature and a little with CO2, given that it's rising. But there are other impacts, and I think I should emphasize that too. There are changes in precipitation. With increasing temperature, the air should hold more water. Many areas will get wetter, but some will become drier. And there are also the indirect influences of increasing bushfire risk and so on. Those have been dealt with by the Climate Commission, the Climate Council, and many other papers in the scientific literature itself. So let's get back to that intriguing idea of performance and think about performance of animals that aren't like us at all. So let's think about organisms that don't regulate their temperature through their internal metabolism. These would be things typically such as insects, spiders, mites, amphibians, reptiles, and they really are somewhat subject to the vagaries of the environment, such that as temperature increases, their performance increases. You can think of this as leg strokes per 20 seconds, but you can think of it as metabolic rate or reproductive output and so on. The way this works is that there's something of an asymmetry in the curve. In other words, below the optimum, things decline quite slowly as temperature declines. But to the right on the graph, things change pretty quickly as temperature goes up. And there's actually quite a close relationship between the optimum where performance is best, and the maximum, kind of where things fall apart. And that has to do with the biochemistry and physiology of the organisms themselves. Ultimately, proteins fall apart if you warm them up too much. What we can think about is what happens when the habitat temperature actually starts exceeding the optimum. This has been investigated by a range of folk, and it's really just called the thermal safety margin. And in essence, when the habitat temperature is kind of over here, then you're either at well beyond the optimum, in other words, you're at negative values based on this very simple calculation. As soon as organisms are there, they're starting to become really troubled by temperature. In this kind of area, which is the amber here, 0 to 5, things are fine. There's usually a bit of space to do stuff. They're well within their optimum. And when the thermal safety margin is greater than 5, you're in this kind of area. And performance does decline a little bit. The slope tends to be quite gentle. In other words, for whatever reason, and that reason is still being investigated, organisms tend to have their optimum quite close to maximum performance. So the question is, what does the thermal safety margin look like at the moment? And that is some research that's recently come out by a range of groups, including some work we have done. And if you look right across the globe, squeezing it into a single line more or less, so this is latitude south here, north over here, you'll see that there's a range of organisms already that seem to be below their thermal safety margin. In other words, they have no space left to move. These are mostly in the tropical and subtropical areas. Some of the tropical organisms here are actually in deep, cool forests. We could talk about them later. This is for reptiles, lizards. No snakes were included here, just lizards. And we see that there's already a thermal safety margin problem there. Some work by Barry Sonervo and colleagues coming out of the US, but actually including scientists in the School of Biological Sciences at Monash, showed that what's happening here is actually what you'd expect. In other words, when they went out and looked at some populations of lizards, they found that they had disappeared. So there is local extinction of populations, which would nicely reflect what's going on here. That should be concerning for all of us. I do notice there's some biologists in the audience, and of course biologists in the audience should immediately think, well, hang on a moment, there's a good solution to this question. The solution was come up by Charles Darwin, right? Organisms evolve. After all, we're quite used to organisms evolving pesticide resistance, almost, well, by our accounts, instantaneously. DDT, flies, no more flies, then suddenly DDT doesn't work anymore. We're quite used to metal tolerance evolving in plants. So the question is, why haven't we seen that kind of evolution going on? Why don't we expect organisms just to evolve in response to increasing temperatures? After all, this is not the first time that the planet's temperatures have changed. Well, that question's actually bothered a whole range of people. And together with some colleagues, we looked at several thousand organisms' thermal tolerances right across the planet, illustrated here by mammals, birds, amphibians and reptiles, and a variety of invertebrates, and we also did some work on trees. And we just asked ourselves, well, if there's great evolutionary potential, we should expect fairly large variance, given that the climate varies so much across the planet. We were quite surprised. The variance in the upper bound, the upper thermal limits, what they can tolerate on the upper temperature scale, is quite small compared with what one finds on the lower temperature end. And it's true not only of the invertebrates and reptiles here, but it's true also of trees and of birds and mammals. There really seems to be not very much scope for movement. In other words, there's no easy evolutionary way out of this conundrum. There seems to be a limit sitting somewhere between about 38 and 48. And you may think in your mind, oh, but what about all those strange Pompeii worms that are at hydrothermal vents in the deep sea and so on? Turns out they're not that good at high temperature anyway either, when they're looked at under the right pressure conditions. So life tends to have a high thermal limit. That's problematic because temperatures are certainly increasing, as the IPCC reports and many scientific analyses have demonstrated. It's not only temperature. I did earlier promise that I would talk a little about CO2, because after all, it's CO2 that's increasing that seems to be at the bottom of all of this, along with some other greenhouse gases. If we were to perfect geoengineering of the form where we might have a sunshade over the planet, or squirt particles into the stratosphere, and so, in consequence, lower incoming solar radiation, we would still sit with 400, more or less at the moment, parts per million of CO2 from a pre-industrial 280 parts per million. And CO2, as you know, for all of those that were drinking fizzy drinks outside, dissolves quite well in water. And as a consequence, we have an acidifying ocean. And that's a real concern. I'm not going to go into a long story about ocean acidification here and how it works, that the southern ocean organisms are particularly susceptible as a consequence of the chemistry. All I would like to do is draw your attention to some recent work from Nature Geoscience and Nature Climate Change. This paper actually documents dissolution of pteropods. These are pelagic mollusk species. In other words, as we're sitting here, they're busy dissolving. This particular work really worried me the most on reading it just recently, in the sense that juvenile krill are very susceptible to ocean acidification. And for those of you who have done any work thinking about southern ocean systems, along with squid and along with some fish, krill, though, are really, really important as the basis for marine ecosystem function in the Southern Ocean. And mind you, we're turning more and more to the Southern Ocean as a resource that needs to be exploited to increase our ability to deal with food shortages. It suggests to me that we may, in the end, see what's a magnificent, highly diverse system under real threat into the future, even if we were able to deal with temperature and not get on top of the CO2 problem. And with that, I think we need to turn to some discussion of solutions.
One of my roles at Monash is as the program leader in this National Centre of Excellence that Andrea mentioned at the outset. And in that Centre of Excellence, which is a large multi-node, so there's several universities involved there, more than 100 researchers and many people cooperating together, very much focused on some of the issues that we need to focus on in order to solve some of these problems. And it's some of the work that's coming out of that group of people that I'll talk about later on in my talk. Stephen and I are going to pass the talking stick over a couple of times here this evening. My first segment, if you like, in that I want to just talk about things that are already on their way, that there are more or less available to us already as alternative energy solutions, and talk about some of the issues and challenges that we face there. And when I say we, I mean not just we as scientists and engineers, but we as a community, because some of the challenges will be things that we all have to face, and I'll explain what I mean by that in a sec. Okay, but let's set the scene first of all. Here is the problem. The problem in Australia is that the majority, this is years, and this is the energy supply that we rely on. And as you can see from the legend up there, it's mostly fossil fuels. The renewables part of that, that's the hydro and wind and solar, has been growing, but it's a relatively small fraction of the total as the total continues to grow. What we do with that, of course, is multifaceted, and that's one of the problems, is that we must remember that there are multiple solutions to this problem required. It's not just about generating electricity by other ways. There are major issues in transport, and it's not just about cars, it's also about trucks, planes, boats, and so on, manufacturing needs, and so on. So there are multiple answers that we really have to strive for in solving these problems. The problem is particularly serious everywhere in the world, and that's including Victoria, where we use brown coal. And so this is a very sad story, shall we say, but it's not one that is just belongs to us. Brown coal is used as the base load power supply in many parts of the world, and it's a pretty serious issue. The issue is simply that it's a pretty ordinary kind of energy supply. It's quite wet. And in the end, by the time you actually get the electricity to burn in your home or to use in your home, there's about a kilogram of CO2 that has been produced in order to give you that kilowatt hour of electricity in your home. And that's a very, very poor number in terms of an amount of CO2 that is produced, and poor as in large number for a kilowatt hour of electricity. So that's the problem that we face, particularly in Victoria, but in all parts of Australia as well. So brown coal is really bad stuff. Can we capture the CO2? You've probably heard talk about capture technologies, and the answer is actually yes. It's quite a straightforward process. There are a number of ways of doing this, and I've written some chemistry down here as to how we can absorb the CO2 into various kinds of liquids. So this is a technology that can and is already being used in power stations in order to get the CO2 out of the emission from the power station after the coal has been burnt. We can do that. That's a definite possibility. But what do we do with the CO2 after we've done that? We can separate it from that gettering agent, that absorbent agent, but where do we put it afterwards? So once we've got our CO2, here are some alternatives, many of them underground alternatives, but these we have to be very sure of as being totally secure. Totally secure, not for a century, not for a millennium, but probably millions of years. Otherwise, if this CO2 begins to leak out or leak into various forms of aquifer and other underground structures, then that CO2 is always there and always a potential danger. So this doesn't feel like a long-term solution to this problem. It's just a way of sweeping under the carpet for a while, and it's also an expensive solution to the problem. It's said that in order to run this whole system of getting CO2 and then putting it away somewhere, for every couple of power stations that we have, we'll need to build a third one in order to supply the energy costs of running that system. Or in other words, your electricity bills are going to go up by about 50% just for this reason alone, if we stick with what we're doing. That doesn't seem like much of an option. There are other ways of using fossil fuels that are coming along. Some of these you know, and this is all about using it more efficiently. Some of these you know, and I won't dwell on hybrid and electric technologies for vehicles, but these are all ways of trying to use our fossil fuels better and smarter so we don't generate so much CO2 in the process. A couple of ones that you may not be aware of, a locally origined company, Ceramic Fuel Cells, has produced a fuel cell that can be used in a home running on natural gas. And this is gaining real traction in Northern Europe, where the idea would be that you'd have a little unit like that in every home, generating electricity from natural gas by a direct fuel to electricity process. And it's very, very efficient, up to 85%, allowing for some of that extra heat to be used for hot water heating in your home. That's a very good concept in terms of using all of the possible energy that's in that gas, in the natural gas. Another related concept is this thing here, which is a micro gas turbine, works very similarly to a jet engine. But it is much smaller, and it's very, very efficient in generating electricity from natural gas. It's more of an engine than it is a fuel cell, but it's also an approach to using that precious fossil fuel much more efficiently. But all of these things are going to cost us more. All of these devices cost more to run. The technology is more complex than simply burning coal, digging it up and burning it, and we're going to have to face that prospect of our energy costing more. It's hard to avoid that in just about anything that we talk about. There is another problem, and that some of these things just don't work in all situations. That phrase range anxiety is being used to talk about how you feel if you're driving an electric vehicle or a hybrid vehicle or a plug-in with a very limited range, and you spend most of your time worrying about next time we can plug in. The range of this thing would probably not be more than a few hundred meters, and it's just not obviously a solution for the needs of that kind of industry, anything that we're talking about here. It's very hard to think how that kind of mining operation or shipping or aircraft are ever going to use anything but hydrocarbon fuels. Not fossil fuels, but hydrocarbon fuels. And I'll talk later about how that might be true, how that might be possible. But to go back to prices, just to put that in the world scene, here are some bar charts showing in Australian cents, in this case per kilowatt hour, just comparing us with other parts of the world. I won't dwell on this too long, but you can see there's a lot of countries there that are paying more for their electricity than we are. The same is true for petrol, and the same is true for diesel. Right? So there is scope, if you like, for us to be paying more. On the other hand, it's a challenge for us as a society to accept the fact that energy prices may need to be a lot higher for just about everything that we do than they currently are. Where can we get some other forms of fuel from? So biodiesel and bioethanol are probably things that you're already aware of as bio forms or renewable forms of these fuels. But there's some real problems here, especially if you start to conceive of these as large-scale supplies of fuels for example, shipping or mining and so on. So it's not hard to do the chemistry from what is effectively a food oil, plant oil, through to a material that burns very much like diesel, can be used in aircraft, can be used in trucks. That's all straightforward. The problems are these, that the economics of that is driving parts of the world into clearing rainforest, which itself is an extremely bad idea in this context, in order to grow food oil crops. So much, and the issue about the impact of that on food supply is so great that not so a few years ago the UN recommended a complete moratorium on that kind of activity in order to secure food supply in certain parts of the world. So the economic drivers here can become a real problem. Let's talk about some of the renewables that we know about: wind, solar, hydro. Perhaps hydro we leave out of this because it's well understood and well known, but wind and solar are definitely becoming more and more part of our energy supply. But here's a problem with it that is growing in parts of Australia and is very, very much part of the issue that's true in Northern Europe, especially Germany. And just to illustrate this, here's a graph of the renewable energy supply. This was a particular month in South Australia. The energy coming, or the power coming from the various sources of renewables in that state at that time, different days, different hours of the day. And what you see there basically is it's all over the place. It's an intermittent source of energy. And to use that in large quantity is extremely difficult for the grid operator and for anybody else who's plugged into the supply. So much so that at times of the day, and depends on the supply and on the demand, at times the power is worthless. What can we do with that energy if we got too much of it, supply way exceeding demand? Then one of the things that can be done is we can use it to pump water uphill. It's not as silly as it sounds, but it is one of the best things you can do with it if you happen to have a hydro dam somewhere nearby, which is not true in South Australia, and not true for most of Australia. So this is not an issue, not a solution for many of us. In Germany, they currently they give quite a lot of their excess energy to Italy to pump water uphill into a dam and then buy it back at considerably greater cost at other parts of the time of the day and the month. The German electricity consumer is extremely upset about that. You might have noticed where Germany sat on my energy cost graphs before. Is electricity in Germany has become very expensive, and this is part of the reason, is that our renewables we can't use as efficiently as we'd like to. One of the answers to that's been discussed in great detail is battery technology. So battery technology is becoming an important part of this story. And just to illustrate the challenges there, let me compare some well-known batteries, the lead-acid battery in your car and the lithium-ion battery that's in your phone or in your laptop. And this number here is an important measure. It describes how much energy we can carry around in a kilogram of that material or that device. And you see my comparator here is petrol. So when you carry around a kilogram, which is a little bit more than a litre of petrol, you've got 47 megajoules of energy available from that. If you try to run the car on a lead-acid battery, you can see the difference here is huge, and therefore lead-acid batteries just aren't a solution for electric cars. Nor are lithium-ion batteries. They are struggling to be better than a hybrid solution. Are there other solutions available for cars and possibly for renewable energy supplies to actually absorb some of that energy and give it back when we need? There are things coming along, and this is one of the things that some of the groups in ACES are working on. It's a magnesium-based battery, and you can see that this number is already a factor of 10 better than current battery technologies, and that's the sort of gain that's needed in order to make some of these things really possible. But when we do that, we begin to realize that in everything I've just been saying, that some of the solutions that we started here, we're now talking about energy, but as we look for solutions, we're beginning to realize that this has big impact on other things like food supply, like water supply, and for us chemists, we have to think very much about the impact of it on raw materials. There's no point in us coming up with a solution that relies on a raw material that is scarce and is going to become very expensive as soon as it's used widely. So the concept of sustainability has become a much broader concept in most of science in recent times. This big picture is constantly at the fore in order to determine what is the right thing to do and where to go, especially from down here in this corner where we come from. And I'll finish up this little section then with a suggestion that a very interesting book when it comes to understanding and thinking about sustainability that I strongly recommend to you is this one by Professor Jared Diamond, who's an academic at UCLA, who writes historically about how societies have chosen in the past to fail or succeed. And he tells one harrowing story after another about civilizations that no longer exist or have disappeared from this planet over the last 2,000 or 3,000 years, mostly by ruining their local environment in one way or other, or running out of an important material that was critical to their survival. Strongly recommend that. And with that, I'll hand back to Stephen.
Thanks, Doug. So Doug has just spoken about Jared Diamond's book, and an important message, I think, from the book, at least in the context of our current situation, is the word local. So these were local societies that had started running out of resources and chose to do various things that ended up in either their survival or their demise, mostly their demise. We're something of a global society just at the moment. So getting back to why we should think about chasing the change, I have some works up here that talk either directly or indirectly about how it is that we might want to choose to live, at least in what we would think of as Western society. And the bottom panel is about the cultural dimensions of climate change. So, of course, we've already dealt with those in some way. We are right here dealing with the cultural dimensions of climate change because we're discussing them, and we've already discussed some speculative fiction that has influenced our culture. What I'd like to do with here is focus on humans, really, in terms of how climate change may affect us. So we spoke a little about the diversity that we share the planet with, and now I'd like to talk about how we are being impacted by climate change. And of course, to begin with, I think we should go straight back to performance. You'll recognize the curve on the left. The curve on the left is actually the curve I showed you from the small ectotherm, the kind of insect species that we were discussing. And the curve on the right-hand side is really something quite different. It's different only in the sense that it comes from a mammal species. And here, instead of the extent of performance, we just have a decline in survival. But you'll notice it's quite shallow towards the lower temperatures. It's much steeper at the upper end. And you'll notice that the optimum or the comfortable space is somewhere between about 17 and 21 degrees. And this, of course, the decline in survival really means an increase in mortality in some sense. There's a double flip here. What I'd like to point out is that the mammal we're speaking about is us. Well, it tends to be people in Manhattan in this paper. And what the authors are talking about is the fact that, of course, with warming temperatures in Manhattan, two things happen. One, deaths from low temperature decline because, well, it's not getting that low anymore. The second point is that deaths from higher temperature increase. The balance isn't zero. There's an expectation of an increase in mortality. The significant point is we're not talking here about the kinds of extreme events that occurred in Europe several years ago, where there were many deaths as a consequence of high temperature summer extremes. These are just regular seasonal mortalities that are encountered in Manhattan. The graph may look a little different for, say, Darwin, but probably doesn't look terribly different for Melbourne. It's not only the direct impact on humans that has been identified, but two major medical journals, The Lancet and BMJ, British Medical Journal, have both identified climate change as a significant health challenge into the future. And these journals are not dealing only with the direct mortality, but they're also thinking about aspects such as changes in vector-borne disease and changes in disease that aren't vector-borne, but of course have higher growth rates as a consequence of increase in temperature, getting back to that little graph I showed you of increased performance. It's true also of bacteria, for example. The BMJ article was particularly interesting because it was a group of military medical folk as well as civilian medical folk talking about how climate change seems to increase conflict and ill health simultaneously. And there are quite a few papers that have been published recently in high-end journals showing that at least in the past, for the areas of history we have good documentation, where there's dramatic climate shifts, you have an increase in conflict. This is something we really need to think about. But it's not only these kinds of dramatic impacts, death, conflict, it also has an impact simply on business. So this piece of recent work that came out, the top left-hand panel that you see there is what things are like at the moment. It takes a bit of explaining, but essentially, if you have a look at these legends, at this temperature it's recommended that you could do 100% heavy work. Think of construction work or similar heavy work. As soon as you get up to these kinds of temperatures, you have to decline to 25% heavy, then it's 100% light, and by the time you're getting to about 33 or so, the recommendation is for substantial light work. This is the military scale. It's a little different. These are some of the impacts out of the recent set of scenarios from the IPCC. This is, of course, the least generous of them. In other words, this is a lot of CO2 going into the air. This is a much more generous scenario. But what you'll see is that many tropical regions end up in this space pretty quickly. In other words, that has a direct impact on business and the work we can do. I found it fascinating in the context of recent discussions with the election that this area had been identified for development by various parties. It's also the area that tends to come up bright red into the future. It's not only temperature, we're also talking about CO2. I'm now going to switch continents and talk a little about the continent from which I recently moved. Under low CO2 conditions, what you find is that in any area that is a tree grass savanna, and many areas are like that, many areas of Australia, many areas of Africa, many areas of the Americas have tree grass savannas. There tends to be broad open grasslands with trees interspersed. Under 280 parts per million, grasses really win because trees need lots of CO2. They need lots of CO2 because they're building carbon structures. So when you have low CO2 environments, trees don't grow very quickly and they tend to be wiped out by grass fires. And so the balance is towards grasses. And that balance, of course, gives you things like the African savannas filled with grazing ungulates. This is a series of pictures from southeastern South Africa. This is in the Eastern Cape, for those of you that know the region. And this is an area called KwaZulu-Natal. It's a tropical area. And you can see a progressive change from grasslands all the way through essentially to thicket and woodland. What's happening based on laboratory studies, on field experiments, and on an assessment of change across various land uses is that increasing CO2 levels mean the trees are just managing to do much better. They just grow out of that fire trap extremely quickly. As a consequence, everyone undertaking extensive agriculture, farming largely with cattle here, is struggling. And conservation areas are struggling that are trying to hold on to ungulates that evolved under more or less a grass balance in terms of the tree grass situation. So this suggests that things are really getting much more complicated. In other words, many of the farmers working in savanna areas are more or less having to obey the lessons of the Red Queen. They have to do all the running they can just to keep up, and more or less they seem to be losing this battle. So that's a further impact, and this is something of a subtle impact. And the reason I say it's something of a subtle impact is that before this work was undertaken over the last 10 years, most of the focus had been on instructing those very farmers to remove the livelihoods from the land. In other words, pull cattle off. It was a consequence of overgrazing. That's why there was a reduction in grass and an increase in trees. Actually, you can do all you want, more or less, at the local level, short of getting out and chopping all the trees down over and over and over and trying to work the seed bank. But local solutions aren't going to work here because you're really fighting 400 parts per million of CO2. The final example is really much more of an example to do with how we experience the world around us. This NCARF report had a graph in it showing the decline in what they call meter days of snow in the Victorian Alps and in Tasmania. In other words, there's less snow, it's not quite as thick, and it doesn't last quite as long. And the work published in the Cultural Studies Review just asked the question of people living in those areas, how do you feel about this? To summarize what's a really quite detailed review is that most of the respondents that were interviewed were pretty depressed. Their whole livelihood was changing. And this is a single example of a very small area of Australia. So in essence, the reason we're talking about chasing the change is that there are very few areas of modern human endeavor where we can't already see impact. And that impact is extremely important to consider in why we need to make the changes we've been thinking about this evening. And with that, over to you.
So I want to go on now to talk about some alternative energy solutions that are a bit further out, that are coming down the line, so to speak. And I love this picture. I think it really illustrates why Australia's got to be front and center in this particular endeavor. This is a map that averages onto a daily basis total insolation from the sun, so solar radiation effectively, over the whole year, over the whole day, in all places, and then puts that on a daily basis. And what really, and of course, brown is the high value, and these blue and purple is much lower. And what, of course, sticks right out is just where and how much of Australia is extremely high solar insolation. Other parts of the world that are important in solar energy, Western China and Tibet, parts of Africa, parts of southwest US, and of course some very interesting ocean areas on either side of South America. Not impossible to conceive of ocean-bound solar collectors of some sort or other. But it's not really possible just to stick huge arrays of solar cells way out there somewhere around Alice Springs for several reasons. We've looked at the intermittency problem, and others that large quantities of energy aren't always going to be available when we need it. And secondly, you can't move large quantities of electricity around without losing a lot of it over thousands of kilometers to the main population centers. So that, as a concept, has got problems. So we want to reach over what you might call present-day photovoltaic concepts and technologies and look at what else might be coming down the track. What else can we do with that solar energy? And remember, of course, that all of the fuels that we're burning today were produced by photosynthesis at some point or other in the distant past, hundreds of millions of years ago. So what can we do today about that? So we want to look at photosynthesis. Can we be inspired in some way or other by what nature has developed as a photosynthesis process and do something with that to guide us as to how to replicate that process? So photosynthesis, in one point of view or one perspective, starts with water. Some of the first and very important steps, and these are much studied around the world at the moment, including here at Monash, oxidizes that water to produce the oxygen and leaves the hydrogen in a reduced form. And I'm not going to say too much about what I mean by that hydrogen. It's just I put it in inverted commas because it could be in all sorts of forms. Right? So that's open to us. And then effectively in a second step, we absorb the CO2 as a plant does and produces carbon compounds from that. One of the important things to observe here is that most of the energy that goes into photosynthesis, it goes into this process much more so than that process. And therefore one of our concepts that can come out of that is that an artificial photosynthesis might start simply by getting this reaction to go purely driven by solar energy, by sunshine, taking water and making hydrogen and oxygen. And once we've got that hydrogen, maybe then we can either use it directly as a fuel, we can ship it around much more easily than we can electricity, and we can use it at some point and some place to make other compounds for high-value compounds. But the hydrogen can be a fuel in its own right. So that's one of the places that we start. Hydrogen is a useful fuel. It's becoming more and more common from a very low point as an automotive fuel. So here are some pictures of vehicles and filler stations in California. This is also true in Norway, parts of Tokyo, where hydrogen-based fuel cell-driven cars are a reality. So hydrogen is a fuel. Problem is at the moment that hydrogen isn't produced by any renewable way, it's produced from fossil fuels. So that just says that we can do something with this hydrogen, but we have to make it first in a renewable way. It's not hard to make hydrogen. In fact, some of you might even recall doing this in high school. It's a very simple experiment. If you can hopefully see this movie bubbling away there, there's hydrogen being formed. We're simply putting a voltage across, a relatively small voltage across a couple of electrodes in some salty water, and off comes the hydrogen and oxygen in the other test tube. In fact, our solar radiation is in fact ideal for this purpose. The amount of energy in a large fraction, not all, but a large fraction of the photons in solar radiation are sufficient or more than sufficient to cause this reaction of splitting water into hydrogen and oxygen to take place. So this is all very practical, it's all very possible. How do we actually make it happen? So one of the problems in making it happen is that we need special kinds of catalysts on both electrodes to make it happen very efficiently, and in particular to absorb the light very efficiently. And in the movie that you see there flicking through, you see first attempts at creating those catalysts and studying those catalysts that can drive water splitting, as we call it, directly from sunlight, or perhaps boosted a little bit with a little bit of power supply externally. And there's more on that topic and more on that video on our website there at electromaterials.edu. So that's how we might make hydrogen. What might we do with it other than using it directly as a fuel? So it's very useful as a fuel, but it can be used in multiple other ways. And here's an important concept that might get us to these fuels that we need for mining, for shipping, for aircraft. So we're probably not going to ever do better than some form of hydrocarbon for those purposes because they're so energy dense. There's this number we had before. If we have hydrogen and we have some sort of form of biomass, I'm showing sugarcane there, not the sugar, but the biomass that's left over after you make sugar from the cane. And we can process those. This is technology that's coming along into a way to make smaller molecules of various forms of sugar. The energy density, remember that number we talked about before, is still very low. It would be very hard to fly an aircraft on bioethanol, for example. It's just too heavy for the amount of energy that you get out of it. What we can do, and this is well-known chemistry, we can take that and we can hydrogenate it using hydrogen and make a hydrocarbon, and there are 48 megajoules returns. What we learned from that bit of thinking is that in fact solar hydrogen can represent more than 2/3 of the energy of that fuel, of that effectively that biofuel. For one perspective it's a biofuel, in another perspective it's a carrier for the hydrogen energy. And if anyone's alive enough at this time of night to do some arithmetic, if you're wondering why those two numbers don't add up to that number, it's simply that one of the problems with hydrogen is that you have to carry it around in various kinds of heavy materials like cylinders, and therefore that number reflects not pure hydrogen, but pure hydrogen in some kind of container. What else can we do with this general concept? Direct CO2 reduction. So now we're trying to, in effect, do better than photosynthesis does by directly reducing CO2 and supplying other materials to it. We expect that we're going to have in the very near future large quantities of CO2 captured from power stations. Can we do something useful with it? Well, if we can photo-reduce it directly, using special catalysts and special kinds of electrolytes, then some of these much higher value materials can be made directly from that in a photosynthesis-like process, but probably a bit smarter than photosynthesis. So hydrogen as a fuel is one of the simplest and cheapest things that we might do with that concept. This idea of artificial photosynthesis is so important that there's quite a big move around the world to create a global project to focus on this, to coordinate multiple efforts in multiple parts of the world to really examine this and to coordinate. And this paper that was published recently from a large number of us in this community tried to make the case, mostly to governments and to other bodies, that this was an important thing to do in the world to form such a global project. I want to finish off with 2 or 3 other kinds of energy concept that are around, where we might get some energy from. And I think all of these different solutions will have an impact somewhere on some kind of aspect of energy use. This one is gaining important traction at the moment. Thermocells, simply the idea of making heat turn into electricity. The device that does this in this is a little bit like a battery, but we don't charge it. We simply heat one of the electrodes up to a higher temperature. And there are useful sources of higher temperature, and I'm showing 2 kinds of geothermal concept here. These red spots are, you probably can't see the axis, but this is 300 degrees C underground in various parts of Australia. So there are sources of geothermal or geological heat that we can use, and with cleverly designed devices can turn that into electricity. That's hopefully coming along in the not too distant future. A concept that's very, very popular in Japan is the idea of a biofuel cell. A fuel cell that makes electricity. The things that are doing it are actually microbes. Microbes that you feed with some sort of sugar, or preferably if it's under your kitchen sink, it'll be from all of the vegetable waste from the house. The microbes consume this, generate some electricity which goes around a circuit there, and so rather than simply using your vegetable waste on the garden, then you can actually use it to generate some electricity. And this could be particularly useful if the source of the fuel could be various kinds of waste paper. Serious concept under serious development in Japan. And then to finish off with, I thought we'd better talk about the big elephant that's in the room, which is nuclear energy. And I won't spend too much time on this slide. Simply, we all know that the big question that's around is this the answer? It's an answer that's being developed in various parts of the world. But we all know that the big question is, what about the long-lived waste? But one of the questions we've got to put alongside that is, what about the long-lived CO2 waste that other kinds of energy generation produce? And those 2 questions are now being lined up side by side very much in these sorts of discussions. I'm happy to have more on that discussion in a minute, but I want to get on to something that is in fact a better prospect. There is a better nuclear fuel around, and I think we're going to see this becoming quite prominent in years to come. Thorium is an element that's just a couple of elements along to the left from uranium. There's lots of it around. It's generally speaking safer to use. Some say that Fukushima would not have happened, the disaster would not have happened if it had been a particular kind of thorium burning reactor. Less waste. It doesn't have the propensity to produce plutonium for weapons. So some of all of those aspects of nuclear energy production go away. It's much more abundant, and in particular in Australia. So once again, we as a country rise to the top of this particular energy story. So probably the greatest concentration of thorium resources are here in Australia. US has lots, various parts of Europe and South America, India. So one of the nice things about that pie chart is that it's spread all over the world. So there's no issue with the geopolitics of energy sources being focused in one part of the world. So I think thorium, and I'm happy to discuss this more as we finish. I think thorium is an important topic for the future. And as you saw on the previous slide, places in India and China, Russia are seriously developing that as a nuclear technology for the future. The question, to some extent for us in Australia, is how much do we support that? How much do we develop, if you like, the technology of the mining and so on that will support that industry? So, just to finish off then, just to conclude, so to speak, what Stephen and I have tried to do tonight is show you some of the serious problems that are arising because of climate change, because of CO2 in the atmosphere and in the oceans, and some of the challenges that we face in developing alternate energy solutions that will alleviate those problems. And I leave you with the thought that I think that Australia has an important role to play in not only leading some of these technologies because of the thorium that is in our continent, because of the rich solar energy scope that we have here, but also because as a wealthy country we've got the scope to try to lead the way in terms of lowering our fossil fuel use and ramping up our use of these other kinds of energy generating solutions. And with that, we welcome any questions, and we thank you for coming along tonight.
I think we do have time for a few questions.
Just a quick one. Lawrence Livermore Laboratory's been working on fusion power. They've got some working models. You didn't mention that at the end. What do you think of fusion?
I think it's possibly the ultimate option for the future, but I think it's probably way beyond our lifetimes, most of us, to see that happen. So I think thorium is what you might call the medium term, but in the longer term, fusion definitely. Now, if you ask me what I mean by long term, I would guess 100 years. Now the question is that soon enough for solving the problems that we presented tonight? And I think the answer is no, it's not. So there's the problem.
I'm curious because the mass extinction which Professor Chown is talking about is already well underway, and yet we're talking about climate change, and most of the mass extinctions at the moment are not yet due to climate change. Most of it's habitat destruction and chemical pollution and things like that. And so I wonder if the chase is maybe not the right chase and that we should be thinking of something else. My own concern is that it's our material and particularly energy use which is destroying the ecosystems, and that actually it's not so much a shift to renewable energy, which I agree is essential and all these technologies are vital, but it's actually a massive reduction in energy and material use which is necessary. And that then becomes a social, political and economic problem.
Absolutely.
And not so much a technical one.
Yeah. Do you want to comment on that, Steve?
Sure. I think that you're quite right, of course, in terms of what's been responsible for most of the recorded extinctions to the moment. Certainly we have huge changes in our environment that are a consequence not of the changes we have effected to the climate, but as a consequence of the things you point out, habitat destruction, invasive species on small islands and so on. I think that doesn't mean we should turn our back on what's coming. You know, that just doesn't strike me as being a smart thing for an organism as smart as ourselves to do. It just doesn't strike me as being that. In terms of whether we should be thinking of a technological change or it's a behavioural change, a socio-economic change, a cultural change, I don't see the either or in the question. I simply think that yes, we have, at Monash we have groups that are working on behavioural change. That's a much harder nut to crack. Part of the cracking of that nut is actually to stand up and say the science is telling us a whole bunch of things, and importantly, don't give up. In other words, don't turn your back on it and say, well, basically we're going to hell in a handbasket, let's just measure the temperature and investigate the weave. So the message is that there's a huge problem. We know what these problems are. We know that there are behavioural and technological solutions required, so let's look carefully at them.
I hope I didn't suggest we should give up. But what I do believe is that in Australia we have to reduce our material and energy consumption by more than a factor of 10.
Can I say that I think I agree with you to an extent. I don't fully, I know you understand those numbers, you've been looking at those numbers. I certainly agree with you that I think we all need to be individually and as a society much more parsimonious with our use of energy in all forms. How to do that, how to actually reduce our energy, quantum if you like, as individuals, is a very tough problem. And the only thing that I can think of personally is to ramp up the prices, but that's a very big socio-economic issue. And I'm prepared to duck when people start throwing vegetables at me for suggesting that. But that is probably, and the problem is that we start from a very low base in Australia that are, as I showed, our prices for energy are very, very low. We are used to a very luxurious situation in terms of low-cost energy. So it's a hard place to start from.
I have to add to that energy intensity is what you're really talking about, and that is a big problem. But I'm also heartened by some of the folk that are in marketing, right? Because they really have to market a lower energy intensity. It's not something that's impossible to do, it's just not very pleasant to do. But then, some of the things that have been marketed so well that we do don't strike me as particularly pleasant either. There are a whole bunch of drinks that you can buy to go to raves, and I won't mention the brand names, that don't taste very nice and are really bad for you, and they have incredible take-up in the market. So I do think that there's some areas here where we're talking about making a change that's slightly unpalatable, but that's quite doable.
I'd just add one small thing. I think the problem is we're trying to sustain the way we live and not trying to live sustainably. And there's a profound difference. I think when we stop that, we'll start to work on the right answers.
Thank you. I have a question just in relation to the efficacy of current renewable energy technology. And I'm not a scientist, so I'll put that out front. But my understanding is, for example, a group called Beyond Zero Emissions, there may be someone here from that group, developed a report a couple of years ago which said that Australia could transition to a pretty much 90% renewable energy supply system based on solar and wind power on a distributed grid within about 10 years for a cost. And the cost was about the same as our defence budget per annum. So, taking into account the fact that we do need to look further into the future, but that the Climate Commission has said this is the critical decade, and we're already 3 years into it, wouldn't it make sense to start deploying the technologies that we have as quickly as we can, while we continue to research better alternatives?
I think the answer is absolutely yes, it would make sense. And I think we could, I don't know about the number that one could target here, but certainly a much greater reliance on renewables is certainly possible, but at great expense. That's the problem. And one of the things that one of the important cost elements is that energy storage solution, the shaving the peaks and troughs off of the intermittency of our renewable energy supplies. So, but that's possible. That's the point. It is possible. I mean, we could all have solar cells on our roofs, batteries in our somewhere else around the house, and we could be pretty well independent. But those systems would cost on average $20,000 or $30,000 per household. And the lifetime those batteries, as you all know, aren't terribly long-lived. So that's going to need to be, those batteries need to be replaced every 3 or 4 years probably. So there's a real cost in this concept, but it is possible. So we just have to generate the willpower and the economic willpower to do it.
Well, with scale, I mean, those costs come down. For example, the cost of solar panels has come down incredibly.
That's true.
We now have 1 million homes in Australia with solar panels. Private investment has been $4 billion on those domestic panels. So, thank you.
Yeah.
I just wanted to ask, do you know of anything that's in the pipeline to be developed to reduce ocean acidity? I had seen mention of attempts to mineralise the carbon dioxide dissolved in the ocean in newspaper articles, but I haven't heard anything about that.
Nothing that makes any sense ecologically.
Can I don't know whether I should take time out with a crazy plan. I think Stephen mentioned somewhere the idea of various large technical approaches to this, and there was one wacky plan which was to fertilize, if you like, shallow ocean areas in parts of the world to create large growths of various organisms, shell-growing organisms, which would eventually die. They're sequestering carbon dioxide as calcium carbonate, sink to the shallow ocean, and therefore sequester some CO2 for us. But it's a huge if you like, that's going to work and not have other ecological consequences. That's the big issue. I think they have, yeah. Yes,
and there have been others as well, some other experiments on iron fertilization. Mostly it's iron fertilization because that's the shortage. And the problem is that in some of them it really does work, but in others there's secondary consumption and the CO2 is just pumped straight out again. So before it gets to the bottom, other things have eaten all the other organisms and just stuck it straight back out into the atmosphere.
We have time just for one more question in the centre there, please.
Allen Ginsberg sort of spoke of, paraphrase the laws of thermodynamics, that you can't win, you can't break even, and you can't get out of the game. In terms of what you're talking about in some of those technologies, a lot of those are fairly dependent upon a fully functioning economic system. Given we're probably looking sometime later this decade, early next decade, of powering over the edge of at least the conventional oil cliff, and there is a fairly direct correlation between net energy and economics. I'm just wondering how you see that transition happening in that space of what's going to be fairly rapid and turbulent economic change, that we can make that progression, because we tend to think of these technologies in terms of business as normal, and we'll be operating in a state quite far removed from business and normal in that situation. And I'm just wondering what either of you thought in terms of how you see that energy future in that, and how we make that transition, or at least start that thinking in that space.
I think one of the first things that could happen, you know, if you think of the time scale of a decade or so from now, one of the first changeovers that could start to happen is the introduction of a greater introduction of hydrogen technology as a fuel. Not necessarily solar hydrogen. I put a large emphasis on that. That technology is further out there. It's possible to use any source of electricity to generate hydrogen. And therefore it becomes a great store of that electrical energy, which you subsequently can use as a fuel in a car and so on. So that's already happening, and I think that could grow considerably, and in our larger cities, not necessarily in Australia, but in cities like New York and Tokyo and so on, I think hydrogen technology is an increasing possibility where the economics will not be such a huge impact. But there will be one thing that we'll all have to get used to in most vehicle solutions: range. That range anxiety slide that I showed was a very real issue, that we're going to all have to get used to the idea that our cars, you know, won't normally have enough fuel in them to run more than maybe 100 or 200 kilometres, not 600 or 700 kilometres. And we just have to get used to that idea and deal with it.
I query your assumptions there in terms of volume, scale, and time frames. You know, it takes about 16 years to turn over a vehicle fleet. You know, you're talking 10 years. I don't know, but it's really challenging.
Well, I think we could talk about this for a long, long time. Have you got a quick question? Okay.
I've got a lady since she worked at the UN and was a climate change consultant, and she said that one of the causes for climate change was that actually when one tree was cut down, we didn't plant a new tree. So I was wondering if there was any kind of legal or international effort to plant trees to do that.
There's a very large agreement called RED that's about reducing the rates of tropical forest destruction and then replacing some of the forests. It varies hugely from country to country what the take-up of that agreement is and the extent to which local legislation actually looks after its implementation. So it's certainly not uniform across the world. And that's true of all agreements that have to do with climate change and virtually everything else that we have, with the possible exception of, actually the real exception of the Montreal Protocol on ozone. That is now the only international agreement that has been adopted and ratified by every country in the world.
Okay, I'd like to wrap things up, and I'll keep my closing remarks very, very brief indeed. Firstly, I would like to thank all of you for coming tonight and giving up your very valuable time. I would like you to all go home and think about how you contribute to climate change and what you actually got out of this lecture, because I think that that's very important. A series like this doesn't happen just overnight and without the help of a lot of people, so I would like to acknowledge the help of the Faculty of Science staff and also the students within the School of Chemistry, because they were behind all of the communications and the refreshments that you enjoyed prior to the lecture. And lastly, I would like you to join me in thanking Doug and Stephen for a mighty fine lecture, a fusion of biology and chemistry together. And I hope that you leave with a sense of optimism and a sense of concern and a sense of challenge for the future in this area of climate change. Thank you very much for coming tonight.